Okay, thanks, Dr. Brina. And
Thank you.
The next one, paper ID 389, titled Identification of melanoma diseases from multispectral dermatological images using a novel BSS approach. In this presentation, the authors propose a new method based on blend source separation to estimate the distribution of the three main chromophores separately, in addition to the shading distribution, which they consider as a full source. Based on more realistic assumptions and applying to multispectral images with at least 4 spectral bands, this new method explores the intrinsic properties of each chromophore. In order to validate this method, they use a database of real multispectral dermatological images of skin affected by melanoma. Let's welcome Dr. Mustapha ZOKAY from Ibn Zohr University, Morocco. Dr. Mustapha, please unmute your voice. Hello. Please unmute.
Okay. Now?
Yeah, I can hear your voice.
Thanks. Thank you for the nice introduction. So, hi, my name is Mustapha ZOKAY, and I'm a PhD student in the Laboratory of Materials, Signal and System Physical Modeling. Today, I will present our work which concerns identification of melanoma diseases from multispectral dermatological image using a novel approach of blend source separation. So, the plan of the presentation is as follows. First, I will do you see my presentation?
Yes, I can see your slide.
So the plan of the presentation is as follows. First, I will start with a short introduction of the problematic. Then I will present our approach to identify melanoma diseases. After that, I will show the result of the test obtained. Finally, I will end with a conclusion and perspective. So, in order to identify skin diseases, we must first know the distribution of the structure of the skin. So the skin is composed of two main layers, which are epidermis and dermis, and contain three main chromophores, which are melanin, oxyhemoglobin, and deoxyhemoglobin. Distribution of these three main chromophores is very important for dermatologists to use it to identify skin diseases. So our objective is to estimate distribution of these three main chromophores in an invasive way using multispectral imaging. Based on some physical laws, we can write the logarithm inverse of the reflectance detected by the camera at wavelength long diameter pixel of coordinate U as a linear combination of the three main chromophores, which are melanin, oxyhemoglobin, and deoxyhemoglobin, which we noted respectively is 1, is 2, and is 3, plus the shading, which we note here is 4, and which represented the variation of the geometry of the skin and also the variation of the incident light, plus a term which we noted here in E, and which is related to the characteristic of the sensor. So our objective is to estimate S1, S2, and S3 from the sole knowledge of their mixture. So this problem is become a blend source separation problem, since it is a post-inverse problem, which means is indispensable to introduce the hypothesis on the source or indexing vision. So we have three main families that are which are independent component analysis and sparsity analysis and non-negative matrix factorization. Different approach has been proposed in the literature to estimate this three main chromophore, and we can classify it into two main families. The first family consists to estimate melanin hemoglobin, which is a mixture of oxyhemoglobin and deoxyhemoglobin using TA or PCA or NMF. The second family consists to estimate the three main chromophores, which are melanin, oxyhemoglobin, and deoxyhemoglobin, using new blend approach and specific equipment. So our method is different from others methods. It consists to estimate the three chromophores and show that are any prior information using only blend separation and for multispectral image. Based on the previous equation, we can see that the term in E has no information in the distribution of the three main chromophores, and we propose to eliminate it using the following hypothesis. We suppose that there are a pixel where the distribution of the three main chromophore and shandik are zero. So we can the new mixer model as XE of U equal combination of the three chromophore plus S4, which is the shading. To simplify our model, we propose to take four multispectral image at four bonds. In the bonds blue, green, red, and infrared. Based on the absorption curve of these three chromophore, we can see that the absorption coefficient of oxyhemoglobin and deoxyhemoglobin is almost zero. So our new mixing can be written in the blue and green as a combination of the three chromophore plus the shading, but in the red and infrared we have only melanin and shading. So our approach is based on three means. The first step consists to estimate the sources S1, S4, which is melanin and shading, and the second step consists to remove the estimated sources from the mixture, and in the third step, it consists to estimate the oxyhemoglobin and deoxyhemoglobin. So in the first step, we use the mixture X and X4 as follow. Then we can write this equation in matrix form. X nu we call A multiplied by S of nu, where X of nu is observation matrix, and S of nu is source matrix, and A is a mixed matrix. We use the hypothesis of independence between melanin and hemoglobin, which is realistic assumption, which means that the expectation of S1 multiplied by S4 equal expectation of S1 multiplied by expectation of S4. Then we use the independent component analysis. We can estimate the sources, which we noted Y of nu, and where Y of G of nu equal alpha G multiplied by SG of nu, where alpha G are scalars. So in the second step, we remove S1 and S4, the source estimated in the first step from the mixtures X1 and X2. We use the hypothesis of independence between melanin and hemoglobin and shandik, which is a realistic assumption. Then we will get the new mixture is Z of nu equal I2 multiplied by S2 of nu plus I3 multiplied by S3 of nu. In the third step, we are interested to estimate the S2 and S3 from the mixture estimated in the second step. We use the sparse component analysis. We suppose that there are areas where oxyhemoglobin is active and areas and deoxyhemoglobin is inactive, and vice versa. So using sparse component analysis and calculate the ratio between mixture, we can estimate the oxyhemoglobin and deoxyhemoglobin, which we noted here Y2 and Y3, where Y2 of nu equal alpha 2 multiplied by S2 of nu, and Y3 of nu equal alpha 3 multiplied by S3 of nu. So in the result, we use a database of real multispectral dermatological image of skin affected by melanoma cancer, which is an open access database. This database contains 30 multispectral image, and to lack of space, we present only one image. They are full out. In the bottom, on the top is RGB color image, and on the bottom are a multispectral image at the red, green, blue, and infrared. So to measure the performance of our method, we use two criteria. The first criterion is is classical visual criterion, which consists to visualize the distribution of the three chromophore compared to healthy skin. Knowing that melanoma is characterized by a high distribution of melanin and a various distribution of deoxyhemoglobin and very low distribution of oxyhemoglobin compared to healthy skin. The second numerical criterion we propose here to measure and calculate the interdependence between melanin and hemoglobin. So the result obtained using our method are as follows. You can see from this figure that the estimated distribution of the three chromophore are in agreement with the visual criterion, since we have a high distribution of melanin as represented in the three-dimensional and when we have a very low distribution of oxyhemoglobin and a medium distribution of deoxyhemoglobin compared to healthy skin. We compare our method with the method of the first family, since this method does not need any specific equipment, contrary to the method of the second family. So the result obtained using the method 3 and 4 are presented as below. Knowing that method 3 is based on ECA and method 4 based on NMF, we can see from this figure that this method estimates a little distribution of melanin, but the distribution of the oxyhemoglobin can be seen here as a mixture of the three sources that are melanin, that are oxyhemoglobin, deoxyhemoglobin, and shedding, and which it does not allow to decide the nature of diseases. So we use the second numerical criterion by exploiting the assumption of the statistical independence between melanin and hemoglobin as presented in the equation, presented in this equation. So using this criterion, we can see from this table that our method is very performant compared to method 3 and 4. Since our method provide in output the estimated sources that are more independent compared the estimated sources using method 3 and 4. So we can conclude that we propose a new approach to identify melanoma diseases by identifying the distribution of its mean chromophore, melanin, oxyhemoglobin, and deoxyhemoglobin from multispectral dermatological image. And the result of all tests carried out have shown that our approach is very efficient. So in terms of perspective, we are interested to validate our new method on other melanoma database. And thank you for your attention. If you have any question, feel free to ask me.